Just gonna ramble on a few minutes, but we'll get wait for everyone to join. But you've come to panel presentation, part of Northeastern Sustainability Innovation Week. The title here, as everyone can see, is Fossil Fuel Buildings that are coming to Northeastern. And really excited to have a group of two of our project teams, members of our project teams come here to really give an overview of the sustainability aspects for these two great projects here in Portland, Maine, and on the Boston campus here. And then we'll have some time for questions. So feel free to throw things in the chat if you want to just have them recorded, but we'll kind of moderate that as we go forward. And just let everybody know, we are recording this, and we will be sharing this with students and faculty. I had a lot of interest, folks who wanted to see this, but couldn't make it for whatever reason. So there's a few folks to introduce, but I think before I go on to that, just wanted to remind everybody that this is part of the Northeastern Sustainability and Innovation Week. There's a lot of activities happening, other virtual panels like this one, as you can see here. And then tomorrow we're actually doing it in person over at the Curry Student Center, which I hope all of you can make it and see some great speakers, meet some a lot of organizations, academics, to see what's going on around campus. And if you have any questions, feel free to contact me afterwards. I can kind of put you in touch with everybody. But without further ado, because we have a lot to cover, I'll let the teams introduce themselves. But I believe we are starting with the RU team. Is that correct? Right?
Yes.
All right. So without further ado, I will take down this. I will stop sharing, and the RU team, please take over and introduce yourselves. Great. Thank you.
Terrific. Hi, Jacob. Hi, everybody. Can you all hear me?
Yes.
Great. And can you see the my desktop here? There we go.
Yep.
Terrific. So I'm going to let my team members introduce themselves. My name's Timothy Mansfield. I'm a principal at Cambridge 7. We're the designers of the new RU Institute at Northeastern. And I'm going to go quite quickly through an overview of the project because we really want to get into the meat of it in terms of sustainability and what we're doing with electrification. I'm going to turn that over to my team from Arup and Haley and Aldrich. Our agenda is that I'm going to do a quick intro. I'm going to turn it over to Hillary. She's going to speak about the MEP systems, electrification, and then on to John and about the geothermal. Very quickly about the overview. The project is located on the former site of the B&M Baked Bean factory site just north of the city. You can see an aerial view. If folks drive up to Maine on 295, you're probably familiar with the B&M Baked Bean factory building. And so the site's about 13 acres. This is the way it looked. We are preserving the main factory building where you see it with the smokestack there. The rest of the site has been demolished and opened up to create this new campus for the RU Institute. The feature building of the RU Institute is the Alphonse Center, which is the curvilinear building you see on the site. The design was in response to the peninsula of the campus itself and also to create a sense of a campus on the site. It also responds to the views out to the ocean, the beautiful Casco Bay, which is to the north of the image here. The project is going to include renovating the Bean building, building a parking garage to the, if you will, the west of the site here, and the Alphonse Center. The Alphonse Center is about 250,000 square feet of an academic building that includes laboratory spaces, computational academic learning spaces, offices, research, and gathering spaces. It's a very robust building, very forward-looking, but it's ground in terms of the materials to very much of its site in Maine and in Portland. We're using granite that's being quarried very close by. And the basic elements of the building are this granite, copper, wood, and glass, all very sort of industrial materials that are used as part of Portland's history. We worked very closely with the Arup team to design the building with a lot of sustainability initiatives sort of involved in the actual facade design. We use parametric architectural tools like Grasshopper, Rhino, Ladybug to help us maximize the, if you will, the performance of the facade with regards to solar heat gain and the glare and basically the heat loading of the building. And this was important as all of this has a huge effect on the systems of how the building operates. So Cambridge 7 used a lot of these tools. We do it with all of our projects, but it was a highly effective tool as we designed the building, specifically the upper volume, but and the lower volume as well. We also were very interested in introducing the technology of mass timber, which is really becoming in the forefront of sustainability. The whole west wing of the building is going to be a mass timber construction. Again, a wonderfully innovative, although it's very old, the use of lumber, but it's an innovative technology in terms of its capacity to take fast-growing timber and make them into structural members. John is going to speak about the geothermal aspects and how we introduce geothermal, but I just want to share with you this rendering. This is looking along the shorefront, the shoreline, which is where most of the geothermal well system has been located effectively. You'll see an image of that later. And lastly, I just want to share with you that we've developed a sustainability charter. In lieu of doing a LEED certification specifically, we collaborated with the city of Portland to develop a sustainability charter that covers essentially essential aspects of sustainability: energy, responsible material selection, occupant experience, as I mentioned earlier about how we manage heat load and glare and so forth, and transportation and tying into the transportation network of the city of Portland. This is just a snapshot of the first page of our sustainability charter. So all in all, the building's incredibly efficient, very powerful in its design, but also very creative in the use of materials. And I'm going to turn it over now to Hillary Williams from Arup, and she's going to take you through the essentially the systems of electrification. Hillary?
Thank you, Tim. All right. We just want to start with, sorry, my name is Hillary Williams. I'm a mechanical engineer, lead mechanical engineer for the project. I work for Arup. I also project manage this for the Arup team as well. And I want to just kind of take a step back and talk about the kind of like the context of electrification of the building. In the Northeast, the grid supply of electricity has been consistently becoming more green with the move away from coal and oil, primarily to start off with down to natural gas and increasing our renewables and hydro. But in the future also it's looking to greenify or become more sustainable and net zero as we go on. So looking at driving towards more hydro and renewables technologies away from natural gas even. So that's kind of a context for with the design of the project. Next slide. So I just want to take everyone through a bit of the process, and I think Tim has already touched on this a little bit with how we push down the energy consumption of a building and look at this holistically throughout the process of design. We obviously have to start with a baseline. This is usually dictated by code. Within the Northeast, I think the codes are pretty progressive when it comes to energy. So we have a fairly high starting point, but we then have to look at ways that we can make improvements over that. And we do that in a staged way, looking at the passive systems like the design of the facade, as Tim has already touched on. And then we look at the active systems within the building, how we're serving spaces within the building, and what is the most appropriate system for the type of space. Then following on that from that high efficiency systems, and energy recovery, and that's where kind of the most of my presentation will be. And then the final tools in the toolkit are renewables and purchasing offsite green energy. And I think that just kind of jumps you through the next couple of slides, which has little captions underneath them. So yeah, the step one is the facade, and then the next step is the active systems, and then finally the renewables and offsite technologies. So next slide. Within this building, we were given in the sustainability charter a target of making this building all electric, which is quite a challenge for a lab building, which is historically one of the most high energy intensive types of building that you can build. So we had in our toolkit, we decided to go with, given that we have a site to work with, geothermal as our first stage of design to do most of the majority of the heating and the cooling demand for the building. And then we augmented that with a second stage and a third stage, both in heating and in cooling of air source technologies such as air source heat pumps, air-cooled chillers, and then for very small proportions of the demand of the building, electric boilers. And as you can see from the slide here, you can see there's the majority of the demand of the building, and that's kind of the yearly usage is covered by the geothermal system, which is the most efficient. And then we are working our way down to less efficient, but possibly slightly cheaper in the first cost and space parameters. So next slide. And I think this slide very nicely kind of highlights the differences and efficiencies that we are working with. The reason why we go with geothermal is it is the most efficient, and that's signified by this COP, that's a coefficient of performance. Basically, for every kilowatt of energy you put into the system, we're getting 8.4 kilowatts of energy benefit. That may seem like an implausible thing. Everyone knows that you can only be 100% efficient, but this isn't about creating energy, generating energy. It's about moving energy from one space to another. So what we're doing is we're taking energy from the ground, on the temperature and the heat of the ground, and moving that into the building, or taking energy or heat out of the building and moving it into the ground. And if you can do that in a balanced way and balance that between your summer and winter, that's a pretty efficient system, and it's a stable system that you can run for years and years. It is also quite an expensive system though. So this is a graph of the heating load across the whole year. So I've colored it in basically to try and show the differences between what is demand and what is load. So the load at any particular point is the peak, basically. What is your peak number? Each one of these little things is the instantaneous load at a given hour of the year. But within that, quite a lot of the year you can see is in this green, which is basically quite a low demand value. And that can all be covered by the geothermal and the heat recovery technology as a starting point. So that's where the 96% demand figure comes from, even though, as you can see there's a kind of, maybe you can't see, but the cutoff is 4,000 there in BTUs. So there isn't only 4,000 of capacity in that system, but that covers you for a large portion of the year. And then you go to a slightly less energy efficient solution, but also one that's a little bit easier to deal with peaks and troughs, and that's the air source heat pumps. And then for the least efficient, where you're using it for maybe less than 1% of your year, you're covering that with the electric boilers. And then the next slide is basically a very similar principle on the cooling load side. So again, we're using the ground source first for the majority. In this case, it's about 50% of the demand, but only 28% of the peak. And then the air-cooled chillers, which is slightly more efficient than an air source heat pump, because it's only ever transferring heat in one direction. So it has a little bit more efficiency there. That's the light blue. And then the air source heat pumps are the dark blue to take the peaks in a similar sort of fashion to the the electric boilers. So that's kind of the principles that we've used. It's relatively complicated versus a boiler. You basically have one piece of equipment and off you go. So we're obviously moving in this direction, and the idea is that because the grid is becoming much more green over time, electricity is really the best way for large building stock to get to net zero. it's already net zero ready by being electrified. And when the grid is clean, then the building is basically taking no carbon from the country, or emitting no carbon to the atmosphere. All right. So I wanted to touch on a little bit for those who may be interested where I see the industry going as far as HVAC. In the last 5 years, we've seen a big shift, certainly based on codes and drivers in the Northeast, and Massachusetts and Maine are two of the more progressive states out there, pushing towards all electric design, in which heat pumps is going to be the basically is the main tool that we have in our toolkit, whether they be water source or air source heat pumps. We're also getting push on global warming potential, which is GWP there. The refrigerants that we're allowed to use, are going to be becoming more and more environmentally friendly, to try and push down the amount of CO2 equivalent we're emitting when there are leaks. Cleaning the grid is the other thing, one of the other things, and then not just focusing on on operational carbon, but also embodied carbon, and that means things like looking at materials like timber to reduce the carbon footprint of the actual building materials themselves, and not just the operation. And I think that with that, I will hand it over to John.
Great, thank you. Thank you, Hillary. So I'm John Castrinas, a hydrogeologist with Haley & Aldrich, and I lead our geothermal practice. Next slide. Yeah, so just one point of clarification, geothermal heating and cooling, which we prefer to call ground source heat exchange, is not geothermal energy. Geothermal energy is places in the American West, Iceland, other parts of the world where you have very high temperatures in the subsurface, 200 to 400 degrees Fahrenheit. You harness that heat to generate steam, drive turbines, and create electricity. Next slide. Geothermal heating and cooling, or ground source, as Hillary mentioned, we're taking advantage of the relatively stable temperatures in the subsurface, 50 to 55 degrees Fahrenheit, extracting the heat value in the winter to warm the building, and then in the summer, taking the heat out of the building and rejecting it to the subsurface, working like a battery for all intents and purposes. Next slide. So the geothermal system comprises a number of boreholes that are typically advanced with a water well drilling rig. These are open boreholes in rock. We install loop piping, which is typically high-density polyethylene piping. It's all closed with thermal welds, so we're not pumping any groundwater. We're not circulating any groundwater. In fact, all of the heat pumps and circulation pumps that are driving fluids through the system are located in the mechanical room. So the result is this is a very low operation and maintenance system. There's virtually no moving parts out in the bore field. So again, good for long-term reliability. And we're circulating either water or a mix of water and glycol to make that thermal exchange. The glycol enables us to lower the temperatures down below freezing, which can be advantageous depending on the magnitude of your heating load. Next slide. So why geothermal heating and cooling works well in the Northeast is for a few different reasons. Hillary mentioned how green our energy grid is with respect to carbon emissions. That makes any electrification strategy better suited than regions that are predominantly coal, reliant on coal for energy, for example. We have fairly shallow rock compared to other parts of the country, either outcropping like shown in the photo to depths of say 200 feet. In other parts of the country, rock can be down hundreds of feet or even thousands of feet. And the reason why that's important is we get much better thermal exchange in dense rock than in overburdened soils, sands, gravels, clays. So the other important factors are our aquifers are limited in size, so poorly suited for open geothermal systems that are actually exchanging and pumping groundwater for thermal exchange. And then the other important factor is our seasonality creates heating and cooling demands to keep the system in balance. Next slide. So what I mean by that is annually, we want a mix of heating and cooling so that, again, the system performs like a battery and we don't have temperatures creeping over time. So in this case, we have temperatures on the y-axis, over time on the x-axis. In the upper chart, the warmer colors, this is an example of a system with much more cooling than heating. So you're rejecting a lot of heat. You're not extracting enough in the winter. Over time, the temperature creeps up above where we want it to be. So our threshold temperatures are typically 95 degrees. Above that, the system really starts losing efficiency. And on the low end, we obviously need to be concerned about freezing. So what we want to see is more like the chart shown in green. There will be seasonality with low temperatures occurring in the middle of winter, high temperatures occurring towards the end of the summer. That's fine as long as over time we don't get this temperature creep in either direction. So it really takes a lot of coordination with the mechanical engineer as well as other trades to get the system in the ground. Next slide. So here's just another example, heating and cooling loads, heating in red, cooling in blue, kBTUs per hour on the y-axis. This is 1 year of loads. The black line represents what is covered by geothermal. And you can see in this example, geothermal covers close to 100% of the heating load. That's what we want because that's where you eliminate the fossil fuels that are used locally to heat a building. But then above that line, we have a substantial cooling load that has to be handled by some auxiliary system. So this would be a hybrid system. Next slide. So what does this look like going into the ground? Again, we have an open borehole with a steel casing. The slide on the bottom shows a driller pulling the closed loop piping off a reel and down into the borehole. That reel is, the loop piping is filled with water to get it to the bottom of the hole, overcome buoyancy. Once it's in the hole, we finish it with grout that is very conductive, good for thermal exchange with the subsurface. And then once that, that pipe is in the ground, we test it to make sure it's leaking. We run fluids through it to make sure that there's no obstacles, that hasn't been kinked on the way down. And then finally, we take an apparatus that's shown on the right here that will impart a thermal load, heat, into the circulating fluids. While the fluids are circulating, we monitor the temperature response. That gives us the thermal properties that support the geothermal design. Next slide. So again, here's just a few photographs from the Ideals site. Slide on the left, this is what we want to see, wide open area, nice and level to access these drill rigs. They're about 40 feet long, very heavy equipment. The second slide over shows the drill rig with the derrick up. That's about 20 to 25 feet high. You see the loop piping on the reel in the third slide over with bags of cement grout to be mixed and installed in the borehole. And this is the loop piping with some temporary fittings for testing on the right-hand side. Next slide. So we will lay these out in a, again, open area. You see the slide on the right. That's the Ideal site with the bay in the background, nice and level, prepped, ready for the drill rig. This, we have, the boreholes are not piped individually to the room, but into the mechanical room, but they're grouped in circuits. We manifold the exchangers from the boreholes into a single pipe. That reduces the number of pipes entering the mechanical room. And again, all of the moving parts, all of the equipment driving fluids through the bore field are in the mechanical room. So no pumps to service out in the bore field. And I think that's the end of my presentation, or our presentation.
Terrific. Thank you, John and Hillary. I'll turn it back over to you, Jacob, and we can keep going.
Great. Thank you, guys. And how many wells have you guys drilled so far?
I believe we're up around 20.
That's awesome. That's great. All right, everybody, write your questions down for the Rue team, and then hopefully some time to get to them. But I want to turn over to Kyler and Caitlin to talk about the multi-purpose athletic facility over here at the Boston campus.
Can you guys see my screen?
Yes,
now?
thank you.
Yes.
Full screen now?
Yep.
Yes.
All right. Hi, everybody. My name is Tyler Hinckley. I'm an architect for Perkins and Will. We're the architects for this project, working with Haley and Aldrich on this presentation. I said I'm an architect, and also I lead regenerative design for our Boston studio. Caitlin, do you want to introduce yourself now?
Sure. I'm Caitlin Tripp. I'm a program manager with Haley and Aldridge. I have a background in geotechnical engineering, and now I serve in our geothermal practice.
All right, let's dive in. So most of you may be familiar with this project. It was a bit in the news last week with the formal press release. This is the Northeastern University multi-purpose athletic facility. So this is some of the highlights here in terms of both an arena, fitness and recreation center, basketball practice facility. It's really replacing Matthews Arena for hockey and basketball and graduation events. We're targeting Living Building Challenge core certification and zero carbon certification. I'm going to hit on some of the strategies today that are incorporated in the project to achieve those goals, from rainwater reuse to lower carbon, embodied carbon strategies, as well as our energy efficiency strategies. And Caitlin's going to get into the details of the geo-exchange system that we have incorporated on this project. So I mentioned this is the site of Matthews Arena, the Boston Arena, over 100 years old. You can see here some of the original entry arch and the building. It's located on the east end of campus, current site of Matthews Arena. There's been a lot of amazing events, sporting events, cultural events on this site. And we're really carrying forward that history on this site going forward for the university. A couple of the things that we'll just highlight that we're really incorporating into the design. So the original arena actually had lots and lots of natural light. It had a skylight above the arena. It had windows. This is, before the advent of widespread use of electricity for interior lighting, right? So we want to bring back some of the light quality into the building. Another unique thing, distinctive of Matthews Arena, Boston Arena, is the real intimacy that the arena feels with the upper balcony. Everybody feels like they're really close to the event. We've got that home field advantage of the doghouse kind of hanging over the visiting goalies for 2 periods, right? And we want to carry forward that similar scale and feel of intimacy. So we're incorporating a similar upper balcony, just with a little better sight lines and enough room for your legs. We're also carrying forward the history of the entry arch. These only remaining elements of that original entryway are the terracotta panels that line the entry arch. And we're going to salvage those and reinstall them in one of the entries to the building. And so everybody coming to this site that enters from the Northeast will get to walk through that same archway that people have been over the last 100+ years. So I'm just going to take through a few slides here to explain how the building goes together. This is a vantage point looking towards the corner of St. Botolph and Gainsborough Street. In the distance, you have Mass Ave. Across the tracks, you can see the Carter School that is going up right now. And so I mentioned that this building is really like 3 buildings. So an arena, it's a basketball practice facility, and it's a recreation center. And really all these buildings would likely want to be on the ground, take up quite a lot of area. But we're in a tight urban site. And so we had to stack them all up. So we have long span spaces on top of long span spaces. And our approach to doing so is to really nest them together. And so we're trying to really take advantage of the multi-purpose nature of this building. And so we stack them all together. We push and pull those volumes to give more space back to the public realm at the ground level, and start to break down the scale of the massing within the context of the surrounding neighborhoods. To kind of further that approach, we round the corners, kind of emphasizing movement throughout the site. And then this is, I think, a really critical move. We're wrapping the entire building in one material. So bringing all these disparate buildings, these 3 different buildings that really are 3 different buildings, we're actually bringing them all together in one envelope enclosure, and creating an integrated building. We still are strategic about how we allow for daylight and views. All these spaces require, very particular lighting conditions, but we want to still maintain the daylight and the view, the connection to the city. And then subtly, we actually do call out those programs. So within that uniform building enclosure, we subtly call out the different textures of the activities within. So a different brick texture at the athletic arena, that's B. Different brick texture for the basketball practice facility, A. Again, another one for the student rec center, and another one for the synthetic turf kind of open space on the roof level. So we're subtly calling out those programmatic elements, but within a larger uniform material. So that's just some of the high level. Here's a section cutaway through parallel to St. Vital Street, so you can see those different programs that are all kind of stacked and nested together, that I explained in the first series of diagrams. We did include a few of the views of the building. This is one as you approach the building on the corner of St. Botolph and Gainsborough Street, the kind of main entry with a covered area for queuing. You can look down that. This is sort of looking down Gainsborough Street at the entry and in that covered area where everybody can queue up before a hockey game. Above that is the recreation spaces overlooking Gainsborough Street. This is the view as you're approaching from Mass Ave down St. Vital Street. This is another entry, kind of a secondary entry to the building. You can just get a glimpse of the salvaged arch that is relocated into this entry, and the stairs that lead you up to the concourses through that arch. This is a nighttime view as you would approach, and you could see some of the activity glowing from inside. I just have a few slides to talk about some of the systems, kind of group these into overarching categories. So I mentioned daylight, just as the other team up in Portland was really looking at how to best utilize daylight. We were doing the same. And to meet the requirements of the Living Building Challenge, we need to make sure that more than 75% of the spaces are daylit of regular occupied spaces. And so we've modeled all of those. We've also, highlighting here, use of 100% FSC certified wood. So there's some mass timber structure in this project as well at the roof, which is not only a low embodied carbon material, but it's also contributing to the approach to biophilic design through the project, and kind of creates that relationship to the old Matthews Arena with the wood decking at the roof. Within the frame or the lens of water, how we're treating water on the project, we are capturing all of the water that falls on this building and routing it into a cistern underneath the lobby. And then we are doing 3 things with that water. For one, we're using that water to irrigate all of the landscaping at the ground plane and at the green roof. So that doesn't use any potable water. We're also using that water to flush toilets throughout the whole building. And then lastly, we're using that water to make the ice that the hockey players will skate on. So the ice that the teams will skate on is made from the rain that falls on the building. Because we're doing all of that with the water that falls on the site, we actually have to bring water from the street into our site and infiltrate it back into the ground, because this building is in the back bay area where we need to make sure that we're infiltrating water back into the ground so that the groundwater levels remain at an appropriate level so that the wood piles don't dry rot. We mentioned some of the embodied carbon strategies that we're employing on the project. I mentioned the CLT timber structure roof, low carbon steel and concrete. So that's being strategic about what kind of steel we use, where it comes from, and the types of replacements for cement within the concrete, and even targeting reuse of the caissons under the existing rink in the future building. And so we're working towards driving down the embodied carbon of the structure of the building in the project. Lastly, I'll just talk a little bit about operational carbon. So this is the energy use of the building. Similar to the RU project, we're utilizing a geo-exchange system. In this case, though, it's under the building. It's a real unique urban site here where we're able to introduce this technology and this system. And what that allows us to do, similar again to the RU project, is a hybrid system where we have ground source heat pumps, air source heat pumps, the waste heat from the ice system, all feeding into an energy loop throughout the building. That system, the geo-exchange system, can cover 80% of the annual heating and cooling load. The rest of it would be covered by the air source heat pumps. And then we do have a large solar PV array on the roof that contributes to reducing our net energy use intensity, or EUI, of the building. And so I'll turn it over to Caitlin here to get into some of the details of our challenges and solutions and process for the geo-exchange system on this project.
Thanks, Tyler. So I'm actually going to step back and talk about where we started with ground source heat exchange, and then move towards what's planned for the new building. So schedule has always been a key component of this project. It's Northeastern's goal to minimize disruption to the programs and events at Matthews Arena. And to start with some background, this colorful drawing to the left is a subsurface profile. It shows that there is soft, unsuitable soils in the top 30 feet, with bedrock roughly 150 feet below grade, in a thick deposit of what's called Boston blue clay between. Based on the scale and the weight of the new building, the new column loads need to be supported on deep steel piles driven to bedrock. And the original approach for ground source heat exchange was to pair the installation of closed loop exchangers on the piles that were being driven to bedrock. So basically killing two birds with one stone, getting your heating and cooling from your foundation system that needs to be installed for support of the building. And this technology is called energy piles or geopiles. And the profile includes a cartoon of a pile installed down to bedrock with a U-loop exchanger attached to the pile. And the photo shows the actual condition of a steel pile with the HDPE U-loop that John talked about attached. So John, Tyler, if you go to next slide. So we tested this energy pile system in summer 2024. We drove 3 steel piles with 7 geoexchangers, and it was a great learning experience. The typical pile driving approach led to breaking 5 of the 7 exchangers during the pile driving process. The pile drivers were able to find an approach that successfully installed 2 of the U-loop exchangers, but they were 80 feet deep rather than closer to the 150 feet. And the approach to pile driving would have taken a lot longer to install each pile compared to a typical pile installation. And since schedule was a key driver, it didn't look like energy piles would be the best solution any further. So next slide. So we pivoted to a traditional drilled borehole solution with closed loop U-loop exchangers. We evaluated exchanger depths from 500 feet to 1,500 feet below grade. And we reviewed all the potential opportunities on the site to create a bore field below the new building. But there were a lot of considerations with abutters, environmental conditions, reusing the existing concrete caissons that needed to be taken into account. And this borehole system is again shown on the subsurface profile to the right. So the boreholes are now being drilled through the soil, overburdened soils, and 650 feet into bedrock. And as John mentioned, the thermal exchange in bedrock is higher than soil. So we're now able to leverage a higher thermal exchange in soil or in bedrock rather than the energy pile system that was using thermal exchange in soil. So the last element was that below grade construction is not perfectly plumbed. The piles in the boreholes both have some vertical or horizontal deviation below grade. So there's a lot of planning that has gone into place so that we can install all these elements in the space below the building. So next slide. Again, focusing on schedule, it was decided to install as many boreholes as possible outside of the existing Matthews Arena and keep it open in the summer of 2025. So there are 35 boreholes planned for this upcoming summer. And then the remaining balance of boreholes will be installed concurrently with the foundations down the line. So next slide. And as Tyler mentioned, this building will house both an ice rink and practice facilities. So the heating and cooling loads are not only from HVAC systems, but also for the ice rink, subfloor heating, snow melt pit, and other elements. And the graph to the right was used to evaluate how much geothermal capacity should be targeted for the project. So it shows on the y-axis the percent geothermal capacity to the annual HVAC demand. And as the curve flattens out, there is less benefit to using ground source heat compared to alternate systems that Hillary outlined. So based on the load profile for this building, it was selected to use ground source heat exchange for 80% of the annual heating and cooling load, and supplemental systems for the balance. So this approach helps right size the bore field to balance the higher cost of the ground source heat exchange system and to maintain that construction schedule. So that's how we came up with it, with determining 46 boreholes would be used to meet that capacity demand. So Tyler, last slide. Thanks. So these are, again, some pictures of the drilling process to install each borehole. They're planned to be installed to 800 feet deep, and install U-loop exchangers and grout them in place. So in September 2024, a pilot program was conducted to measure the thermal conductivity of the ground and validate that 850 feet was possible at this site. And based on those results, we're planning to remobilize to the site this May and drill the remaining 35 boreholes outside of the arena.
Yeah, I mean, I just lean in here a little bit. I think that of all the other projects where we've done geo exchange systems, they're usually out kind of separate from the building. They can go on their own path. They can be installed as the building is going up or kind of not impact schedule. And it's been such a driver here to work with the constrained site and the constrained schedule. And I think that the iterations that we've gone through with Caitlin and her team, the university, Suffolk Construction to explore these different options, test them so that we have data to really inform the decision-making process, and then be able to pivot to a better solution. And again, comparing the different options on the table and finding a solution that was better from a performance point of view, from a cost point of view, from a time point of view, through the process. So I just, it's a really interesting challenge, and appreciate the support of the university to really champion this innovative approach. I think that's it for us.
Thanks, Tyler.
Thank you very much, Tyler and Caitlin and the RU team. I know I'm very excited about this project and what we can, what it demonstrates here for Northeastern. So, actually, when are we starting to drill this summer? Over.
As soon as graduation's over.
All right. So if you guys are still around campus, you can come with everyone witness all that. So open up. We got about 10 minutes or so for questions. Please throw them in the chat. Raise your hand. Calling you. I'm always available. If you have follow-up questions, I can connect with this team. Just in the interest of time, just give me the questions and I get answers for you. So thoughts, questions for the team here, for the panel? All right, you guys answered everything apparently.
Okay. I'll ask one then, Jacob, if you don't mind.
Of course.
Just wondering, I know our multiple or multi-purpose athletic facility had an issue with infrastructure, if you will, electrification and the power to our site. I didn't know if RU had a similar experience, if the utility company can provide adequate power for you to electrify that campus.
It's a very good question. The answer is we had to work pretty closely with CMP, the power source up at the campus. As a working industry, the B&M baked bean factory was there. There was a sort of inherent infrastructure already on campus. We've had to work with them closely, but it's worked out in the end. It's complex whenever you're tying back into an infrastructure, right, with a new project of this scale. And the interesting piece of this is that this is really phase one of the campus, right? The Alphonse Center is the major building along with the garage, but it's envisioned in the future to have 2 or 3 other buildings over time, potential residential buildings, potential other laboratory buildings. So, having a robust infrastructure to the site was important, and CMP's been a good partner in that. Yeah.
I would be curious to hear maybe a little bit more about the issues with utilities being able to supply the electrification needs for the multi-purpose building, if anyone could speak to that.
Jacob, do you want me to take that?
Do you want me to it? Sure. We're actually the university campus has a number of some switching stations, kind of so where we have basically our own little grid. So we get big feeds from the utilities, and then we take it and feed most of our grid. So our internal campus is all on a kind of our own grid, and we have some just capacity issues with that. The two feeds that we have are at capacity. So this is actually a great opportunity for us to add additional capacity to our internal grid. So there is a spot, you probably noticed those electrical in this facility that we are going to get more electricity from the utilities for our space that allow us actually to do maintenance on our existing stuff a lot better. But in terms of overall capacity in the local grid, the utilities have said that they have the capacity for us at this time. So in terms of the next steps and the expansion of electrifications in our neighborhood, we'll see what kind of where that comes up. But we've had good conversations with our utilities, and they are ready to supply us with that at this point.
Thank you.
That was a great answer. I was actually asking if you wanted me to answer it, but you just went ahead and answered it.
Sorry. I gotta do something around here. You guys don't
No,
know.
well, it's a very interesting question because it actually had a huge impact on our project, right? It's a very large amount of space with very specific requirements. And also, our project located where it is has, the biggest risk from a resilience point of view to our project is stormwater flooding. And so we've strategically located all, major equipment on upper levels of the building. And so the large switching station that we now have in our building is on a second floor. And so that just creates an interesting, architectural, electrical challenge to fit it, service it, provide access. But it will serve as a real resource to the campus. It will serve our building, obviously, but it will serve the rest of the district and help alleviate some of the capacity issues.
Thank you. That was really interesting.
Tori?
Thanks. These are really great presentations. Have a sort of a follow-up to Amy's question. Love how much of the base load is covered by Geo, and wondering what are some efficient solutions to address that peak without stressing the grid. Sorry, none of the systems seem quite as efficient when you get to the peak temperatures. So how do you, what's sort of the best solution at that point, particularly if you're looking to not stress the grid too much?
Shall I take this one, Jacob?
Please.
Yeah, I think what we were trying to do is actually, be very, very strategic and make sure that the least efficient was doing, less than 1% of the overall heating load for the building with the electric boilers. But the one thing with an electric boiler, it is relatively cheap and space efficient as far as, not making the mechanical systems, take over the building and lose your net to gross. So there is some constraints with regard to, the space that you need within the building and the expense. And, the heat pumps are more expensive, definitely, than an electric boiler, but obviously much more efficient. Although their efficiency in heating mode does drop as the air temperature drops on air side, which is why the geothermal is so great, because it's much more stable temperature. So I think it's having that mix and understanding, where your peak and your demand, peak versus demand is, that helps you kind of tune that. And we felt that we have two relatively small electric boilers that cover like 1% of the demand of the year, and that's how we keep the loads lower, and then do most of it with the more efficient systems wherever we can.
So
Anybody else?
maybe a quick follow-up to that, just on the demand side, for the arena project, multi-purpose arena project, are there opportunities to make ice at low demand times and other ways to balance the load?
So I'm going to speak. I can take this one, Jacob. That's all right.
Of course.
I'll try. I feel like I'm jumping a little bit out of my area of expertise here, but the ice demands are when you're, running the Zamboni or when you're making ice. You can't really, do it off time, right? You use that when you need it. That's when the demands really are. Can we think about, sort of storing energy or, taking advantage of some of those things? Sometimes we can. I'd say in this project, we have a lot of heat recovery, energy recovery.
Okay.
So we're taking advantage of that. There's a lot of ventilation requirements. So as an athletic facility, so we certainly are. But for the ice, you got to, the load is when you're making the ice, when you're running the Zambonis or when you're making the ice. I'd say like when you make the ice, when you make it, which really only happens like once a year, that you could be strategic when you do that. It takes a while anyway.
Yeah, thank you.
Yeah, I would just add, Tori raises a good point, and Hillary can speak to this much better than I can, but I know one of our larger projects in Boston where the ice is used exclusively for thermal storage, they're doing exactly that. They're taking advantage of when the rates drop off in after hours, so to speak, and then using the thermal storage when rates are back at peak. Very strategic, and I guess it's working pretty well.
Yeah, I guess I could have put that on my list of future advancements is having some sort of thermal storage mechanism like an ice storage. That is something that we didn't use on this project. I think we were using geothermal, and maybe sometimes it's an either or, and it doesn't make sense to do both. But I think in the case of an ice rink, you would be trying to use the ice for your thermal storage when you wanted to actually skate on it. So that might not have been an ideal situation.
All right.
Just wondering too sorry, Jacob, just
Sure.
wondering on the pumps, right, for our geothermal. I assume they're connected to emergency power. I was just wondering what percentage of the emergency power that, or how much more does that add to the size of our generators moving forward?
On the RU project, we connected a number of them. I can't remember exactly how many of the geothermal and the electric, so that we had a little bit of resilience of something that didn't worry about air temperature, and then the geothermal, obviously, which also doesn't worry about air temperature. So the two maybe more resilient of the two technologies, and I don't think we had the air source on the generator for that, for the reason that it's a higher load, and then you maybe not a guarantee at all times.
Similar for us, and also the MAF has a place of refuge as a component of it. So larger number of people that can gather there in the case of an emergency. So yes, there's definitely components of the system that are on that emergency backup power. But if I recall correctly, again, stepping a little out of my area of expertise here, it is actually strategically targeted more towards the geo system because it's, air source heat pumps might not work so well in the winter if it gets really cold. So we can because we have a hybrid system, we can divert the needs to the geo exchange system, can leverage that.
Great. Thank you all. Please try to share, but I guess it didn't work too well. But please email me if you have any questions, follow-up questions, want to get a hold of anybody. And thank you all for coming and learning a little bit more about these two wonderful projects. You'll be hearing a lot more about them as they get completed and go up. But glad you all could learn a little bit more. And thank you all to the presenters, the project teams. I know how hard you guys have been working on all this. This is very, very impressive to see the
Very
least.
exciting.
Thank you very much. We enjoyed it.
Yeah, thank you,
Thank
Jacob.
you.
Thank you, Jacob.
Thank you
Thank you,
all.
everyone.